So let's see here. Let's get this raised up a tiny bit. So we'll definitely get to that question that you asked, but I just want to say a couple things first. All right, where'd you go? So a few things, just as a reminder in general. To find the directional derivative of, say, f of xy at the point P, which we might call maybe x naught comma y naught, in the direction of the vector v, we calculate the following. Typically write it as d subscript u of f. Yes, I know I'm writing u instead of v, it's okay. And that's going to equal the gradient of f evaluated at the point x naught comma y naught dotted with the vector u, where u is the unit vector that is the vector v divided by its own magnitude. So that's how you calculate the directional derivative. The gradient, plug in the point, dot it with the unit vector in the direction that you're going. Let's do one quick example. And actually I should point out, just so everyone's cool with this, the gradient of a function, once again, is just a, oh, I should write it as a vector with a little arrow over it. The gradient of a function is a vector, and it's the vector that is the vector consisting of partial derivatives. And just because I should say it, just so everybody knows, I'm going to say it a lot. The gradient of a function always points in the direction of steepest ascent. Meaning, if you are climbing a mountain out on a hike, and you ask yourself, well, I'm hiking in the world, you know, having a good time, it's pretty out, mountain taste, you know, maybe that's the thing. You're on the hill, and you suddenly ask yourself, I'm thinking about 17C, which direction is the gradient? The gradient is the direction that is going to go up the hill the fastest. So if you're thinking about the gradient out in the world, it's just which way can you go up this slope in the fastest way possible, or what direction is the steepest. So, for example, sure, let's say we wanted to find the derivative of f of xy, welcome, equal to, sure, the natural log of, what I got here, 7x squared plus 4y squared in the direction of the vector. Sure, let's make it nice and easy. We'll say v is the vector 3, 4 at the point. Sure. Sure. 2, 5. All right. So we want to calculate this thing. So this does become very just rote in that you are just doing a thing, plugging stuff in and getting a result. Like there's not really a lot of thought involved after you've done it a number of times. So first thing, gradient. So my gradient here is going to be del f del x, del f del y, which is going to equal, okay, so the derivative of this with respect to x is going to be 1 over 7x squared plus 4y squared times the derivative with respect to x, which is 14x. Partial with respect to y is going to be 1 over the stuff times the derivative of the stuff, which is 8y. That's our gradient. And then we want to plug in our point as well. So the gradient at the point 2, 5 not going to be very nice, but we're going to get, let's see. 14 times 2 is 28 over, I picked not great numbers here. Let's see. 7 times 4 is 28 plus 4 times 25 is 100, so 128. That seems right, I think. And then 8 times 5 is 40 over 128 again. There's our not very lovely looking gradient. And now our directional derivative, well, the direction we're going in is the direction 3, 4, but we always have to normalize it or make it a unit vector. So our unit vector u is just v divided by its own magnitude. In this case, v is a 3, 4 vector. Its magnitude is 5. You're going to see that a lot. But just to point out, the magnitude of v is just the square root of 3 squared plus 4 squared, which is indeed 5. So our new unit vector u is going to equal the vector. I would probably write it as 1/5 times the vector 3, 4. But other people like to write it as 3/5, 4/5. Either way is fine. And of course, I've done all the work, but not left myself enough room to actually write the answer. So I'm going to go to another page of paper here. And we'll get that our directional derivative, which we typically write like this, is equal to our gradient at 2, 5 dotted with our vector u, which is going to equal 28 over 128, 40 over 128, dotted with 1/5 times 3, 4. And if I was doing the computation here, I would probably make my life a tiny bit easier and pull out those 1/128. So I'd probably actually write this as 1 over 128 times 1/5, just pulling out those constant terms. And then I have a 2840 dotted with a 3, 4. That seems a little bit less terrible to me. So that's going to be something like 5 times 128. I'm never good at 5, but I'm good at 10 and dividing by 2. So multiply this by 10, you get 1,280, and then divided by 2, you get 640. That's 1 over 7. Yeah, that's right. Okay, 640. And then we're dotting these together, and we're getting 28 times 3 plus 40 times 4, which is some god-awful number. I don't know. It's something. Let's see, 60, 84, 84 plus 160 divided by 640, which, sure. I'm sure that reduces. I don't really care. Question, Erica.
I've always been doing 1 over but I don't know why.
Well, so if I'm so typically, like for example here, our vector was 3, 4, right? And if I want to normalize it or make it a unit vector, I'm going to do the vector divided by its own magnitude, which is 5 in this case, right? So you could totally write it, although it becomes a little unwieldy. You could definitely write it as the vector 3, 4 divided by 5. But instead of dividing by 5, I'm just going to write times the reciprocal instead because it's easier. Now I could write this as 1/5 times the vector 3, 4, or I could even distribute it in, although I don't like to, and write it as 3/5. Cool? Yeah. Other questions about this before I ask 2 more important questions here. But do I really want to do it for this one? It's kind of interesting. Okay, so here's a question that might seem hard to answer, but it is not. So the question I want to ask now is, for the same function, still for f of xy equal to the natural log of 7x squared plus 4y squared at the point 2, 5, in what direction does the function increase the most rapidly? not the mots, the most. Or in other words, in what direction is the derivative the greatest? Or in other words, in what direction is the slope the steepest? Anyone want to venture a guess? Starts with the G. The gradient. So when someone asks, in what direction does the function increase the most rapidly, or in what direction is the derivative the biggest, or in what direction is the slope the steepest, they're asking you for the direction of the gradient. Now let's be super duper careful here. Even though I would really, really like to answer it this way, the answer is technically not just what we found for the gradient before. So I'm going to point out that the gradient we found before at 2, 5, assuming I did things correctly, is 28 over 128, 40 over 128. But the problem with this answer, as you might have ascertained, is that there's a lot of answers that point in that same direction. You could do 28, 40, that points in the same direction, or 14, 20, or 7, 10, right? All those vectors point in the same direction. And I don't want 100 students giving me 100 different answers. I mean, I don't. Like, you're a teacher, your program that is designed to accept one right answer and not a lot of wrong answers doesn't want to have to deal with 100 different right answers. So the way we kind of make it uniform is we say, well, if you're giving a vector, or if you're giving a direction vector as your answer, we should all have our direction vectors have a length of 1. So whenever someone says, what direction does the whatever do the whatever, your answer should be a vector of length 1, a unit vector. So if you have a vector that isn't length 1, or even if you do, you're not sure if it's length 1, all we have to do to that vector is divide it by its own magnitude. Now, I'm going to show you how this one's terrible, and then I'm going to show you how to make it easier. So let's check this out. Here's the answer I really, really don't want you to give. So answer, it's going to look terrible. It's this vector. Cool, I don't even want to write this down. It's so awful. This vector, 28 over 128, 40 over 128, divided by its own magnitude, which is the square root of 28 over 128 squared plus 40 over, I don't even want you to write that down really. I just think it's awful. There's a better way. There's a much better way. So let me show you what I mean with the picture. So here's that direction. And let's see, direction. Let me think for a second. So that direction is 28 over 128 in the x direction and 40 over 128. So 28 over 128, about 1/5. 40 over 128, about 1/3. So I mean, it's like a tiny little vector here. Right? I'm like kind of going like, ugh. There's my vector. There's my gradient of f at the point 2, 5. But the point is, it's probably not a vector that's a length 1 vector, almost for sure. So instead, what I'm going to do is instead of normalizing that vector, where I have to do this stupid calculation here, instead, what I should really do is make my vector nicer before I normalize it. I know I did this last time, but I just want to make sure everyone sees it. Instead, take any multiple of this vector you want. So like maybe I'm going to take 128 times the gradient, which is equal to just the vector 28, 40. Or even maybe divide that by what? I can divide each of those by 4 and still have it be a nice integer. So maybe I'm really going to do 128 divided by 4, which is 32 times my gradient. You don't even have to write this part out. All you have to be able to do is see that the thing you're writing down is a multiple of the vector you already have. So that would be, divide that by 4, 710. So great, that vector 710 points in the same direction as this vector here. It's 32 times bigger than it. I can't quite draw that, but there's the idea. There's your 32 times the gradient of f. And you know what? They point in the same direction. You know what else? If you make them both have the same length of length 1 by dividing each of them by their own magnitude, they're literally going to be the same vector. So instead of normalizing this vector with all this terrible looking fraction squaring stuff, instead what we do is, or at least what a person who doesn't want to do all the terrible math does, is they're like, oh, I'm going to use this vector here, and then I'm going to normalize that. So the actual unit vector I'm going to write down, instead of this garbage up here, is going to be the vector 710 divided by the magnitude of that vector, which is the square root of 7 squared plus 10 squared. Or in other words, 1 over 104 square root of 149 times the vector 710. And that is a much, much nicer answer than that. If you do all the work here, like if you actually multiply this out and simplify it and do some multiplying fractions and stuff, you'll get this to look the same as that. But I don't want you to do all that work. You don't want to do all that work, right? No one should want to do all that work, really. So if you're ever having to get a direction vector and the vector you're looking at is awful, make it look nicer before you normalize it. So just one more quick example of this, just because I really want everyone to take this to heart. If I said, wow, that's supposed to be an n. It doesn't look like an n. If I said normalize the vector, I don't know, 8 over 23, comma 15 over 23. Instead of doing that, you should normalize instead 815. It's going to be way easier. So the normal vector, the unit vector, and normalizing is the name of the process where you find a unit vector in the same direction. So our unit vector is going to be 815, the vector 15 divided by the square root of 8 squared plus 15 squared, which actually ends up being 17. It's the square root of 289, which is 17. So it's ends up being just 1 over 17, 815. Or if you like, 8/17, 15/17. So two things here. Again, one, you're going to normalize something, make your life easier, and make it easy before you have to normalize it. And two, definitely the more important idea that we talked about here is that the gradient, the vector, the gradient points in the direction of steepest ascent, or in the I always mess up these words, or in the direction where the function increases the most rapidly. And as a bonus, if we ask the question, in what direction does the function decrease the most rapidly, you just turn around. So if, for example, if this was the answer to the first question, where what direction does the function increase the most rapidly, and then I ask the follow-up, okay, what direction does that same function decrease the most rapidly? All you have to say is it's the negative gradient. The answer is negative gradient divided by its own magnitude, because we want it to be unit vector again. So in this case, it would be the negative of that answer right there. Negative 1 over root 149, 710. Because all you're doing is, instead of going up the hill, you're turning around and going down the hill in the opposite direction. Still super steep, or as steep as it gets. And I feel like I have to say one more thing. Sorry, there's one more thing I have to say here, which is not terrible. The other thing we like to ask is, okay, you find out what direction you're increasing the most rapidly. What is, let's read the words here. What is the maximum rate of change? What is the most you're increasing by? And the answer is the magnitude of the gradient. So the gradient, the vector, tells you what direction you're increasing the most rapidly, and the magnitude of that gradient is how steep the slope is. So in this particular case, sure, we asked right here, what is the maximum rate of change? The answer is just the magnitude of the gradient. which is kind of terrible to have to find in this particular example because my numbers are so gross. Sorry, so I will point out, it's not this nice number here. You actually do have to go back to your actual original gradient and find the gross thing. So, okay, that's one disadvantage of doing it this way. So the answer here would be this terrible number, right? The square root of 28 over 128 squared plus 40 over 128 squared. So I will admit, sometimes you actually have to use your maybe actually gross looking gradient and find its magnitude. So often what will happen is they'll ask you to find the directional derivative somewhere like we did. Then they'll ask you to find the direction of steepest increase, which is the gradient divided by its own magnitude. And then you've already essentially done the work to answer the last question, which is what's the maximum rate of change? And it's just the magnitude of the gradient, which you already found when you had to divide by the magnitude of the gradient. So don't do the same work twice. You already found the magnitude of the gradient to divide by, recognize that that is your maximum rate of change and just use that. Again, I kind of skipped over that here doing it the way I did it, but it's fine. Questions about any of this before we look at that homework question that was asked about? And then we'll get into the other stuff. The gradient is kind of the answer to all of it. Okay, so there was a question, and we did do one kind of like this last time, but I'm happy to do another one like this, where you're given kind of a lot of pieces of information, have to figure out what direction what your gradient is. So here is the setup. Consider a function that we don't know. So we have an unknown function of two variables. And we know the following. And we're at the point 5, 2. And we know that, I'm just going to read the words, at the point the function has directional derivatives. We know that the directional derivative, so the directional derivative, which we know how to calculate, is equal to 6 over the square root of 40 in the direction, they write parallel to in parentheses, but that's really kind of not necessary. So I'm just going in the direction of, that's a curious point there. Oh, are they doing that really? Let me think here for a second. I'm curious, and I'm not sure. I feel like that is written as a point, not a vector. At least in my like the way. So the way I see it written here, it's written in the direction. So maybe I can see why they would write it this way: parallel to 6, 2. And I don't think. Oh, that's extra. Wow. There's a reason why I'm concerned by this, because the numbers look like they're supposed to work in a way that that's supposed to be a vector, not a point. But it's written like a point, and there's wow. Okay, let's do it both ways. So I'm gonna do this one way, like I'm gonna pretend like this is the way I think it actually is. I'm gonna say this is a vector. But then we'll do it the other way and we'll say it's a point. Because I'm really not sure which way it's supposed to be. And you should try doing it both ways, depending on if the first way you do it works, great. If it doesn't, then you have to do it. So we know it's that. And then the other one is it's also equal to 3 over the square root of 34 in the direction of, or parallel to, the vector 5, 3. Okay. So let's see what happens. We know how to calculate the directional derivative. So our directional derivative is equal to the gradient dotted with the unit vector. So for this first one, our directional derivative is 6 over the square root of 40. And it's equal to the gradient, which we don't know, but we do know that the gradient is just the vector of partial derivatives. So it's going to be the partial with respect to x at the point 5, 2, the partial with respect to y at the point 5, 2. because that's all they're asking you to find in this problem, right? They're asking you to find the gradient at the point 5, 2. So this vector here that we don't know, this is what we want to find. And then we know that to get the directional derivative, you're taking that gradient and you're dotting it with the vector that you're going in the direction of. Now, if this is a vector, then we need to normalize it. So it's going to be the vector 6, 2 divided by its own magnitude, which is 1 over the square root of, sorry, we're not dividing by 1 over. We're dividing by its own magnitude, which is the square root of 40. The square root of 36 plus 4. So here's what we've got. We have that 6 over the square root of 40 on the left equals the partial with respect to x times 6 over root 40. So partial with respect to x times 6 over root 40. I didn't write fx at the 0.52 because it's a lot to write. We know it's at the 0.52. And then plus partial with respect to y times 2 over root 40. Okay. And then we're going to do the other thing, which is that I'm off page here. So then the other piece of information says the same sort of thing, that the directional derivative in this direction is equal to that. So 3 over root 34 is equal to my same gradient dotted with now this vector. So 5, 3 times, or sorry, divided by the magnitude of that, which is the square root of 34. So, by the way, this is what makes me think they might be vectors instead of points, because the magnitudes happen to exactly match up with the things you already have as your denominators over here. So that to me was the indicator that, oh, they might be vectors, not points, even though they're written as points. I don't actually know them. So we'll do it the other way just to kind of clarify. Bless you. So here we're going to get 3 over the square root of 34 is equal to fx times 5 times 1 over root 34, or fx times 5 over root 34, plus fy times 3 over root 34. I feel like these are not going to come out very nice. I think it might be the other way. Well, let's go ahead and solve this. So here's what I've got. So actually, first of all, looking at both these equations, we can totally multiply both sides by their denominators. So this equation, instead of saying 6 over this equals fx times 6 over that plus fy times 2 over that, let's just multiply everything by root 40 and say we've got 6 equal to 6fx plus 2fy. And same deal here, multiplying everything by root 34, we've got 3 equal to 5fx plus 3fy. And then you can either solve for one and plug it into the other, or do the thing where you eliminate something. I like eliminating better. So I'm going to multiply this by 3, this by -2 to eliminate the fy's. I'm going to get 18 equal to 18fx plus 6fy. I'm going to get -6 equal to -10fx minus 6fy. And then we're going to add them together and get 12 equal to 8fx plus 0fy. So fx is going to be 12/8, which reduces to 3/2. And then you can either plug that back into the other one to solve for, I'll plug it back in. So then plugging that back into this first one or the second one, you have 6 equal to 6 times 3/2 plus 2fy. So let's see, that's 9. So 6 minus 9 equals 2fy. So -3 divided by 2 equals fy. So our gradient at this point, according to this calculation, is the vector 3/2, -3/2. That's how you would answer that. Now, just to make sure we've covered all our bases, it might have been the case that instead of saying you were going in the direction of this vector and in the direction of that vector, you might have been going in the direction of that point from that point. which would also make the calculation, or actually would make the calculation probably even easier. So let's just see what would happen if instead that was the case. So if instead we're going from 5, 2 to 6, 2, well, that's just traveling. That means our vector is literally just the vector 1, 0. So if we're doing this calculation, what we're saying then is our directional derivative 6 over the square root of 40 is equal to our gradient, which again, we don't know, dotted with this vector. And it already is a unit vector. Got a length of 1. That makes it really easy to calculate fx, right? Literally, you're just going to get 6 over root 40 equals fx plus 0 fy. So fx equals 6 over root 40. To me, this feels less likely to be the answer just because it feels too easy almost, but either way could be correct depending on what they actually meant there. In a similar way, you would calculate the other part by saying 3 over root 34 equals your gradient dotted with, well, if we're going from the point 5, 2, whoops, you can't see anything I'm pointing to, sorry. We're going to from the point 5, 2 to 5, 3, you're just going 1 in the y direction. So your vector is the vector 0, 1, which is going to lead to us saying that 3 over root 34 is equal to fy. So my gradient in this particular way of envisioning it would be 6 over root 40, 3 over root 34. I feel less like that's the answer, but I don't really know. Because again, the way it's written, at least what I've got right here, is they're written in parentheses, which makes me, usually that's what notation we use for a point, not for a vector. Although it could be for a vector because, but yeah, I mean, I don't think it's for a vector. So I would try whichever way you think it is. And then if that's not the right answer, try it the other way. I will point out that whatever your numbers are, if it's kind of like this second situation, you probably are just going to end up getting fx being whatever your first directional derivative is and fy being whatever your second directional derivative is. So it should be relatively straightforward to test that as one of the possible answers. Okay. Let's talk about finding maximum and minimum values of functions of multiple variables. And before we do that, I just want to point out, I'm going to just show, whoops, drop papers. I want to show you a picture that I'm trying to draw for you. So here's the picture I want you to see. That, yeah, you can see it all right. Like that. Let's zoom in a bit. Cool. Brighten that up. So basically the idea is that if you have a surface, you're trying to find whether there's a maximum or a minimum or a saddle point. What's going to be true all the time is that at a critical point where you have one of these three things, the plane that is tangent to that surface at that point is going to be horizontal, meaning the directional derivative in the x direction and the y direction. In fact, actually, in every direction, we're only going to the x and y direction, all those directional derivatives should equal 0. Or in other words, to find or identify a critical point, we are going to set each of the partial derivatives equal to 0 and find all the solutions. Or in other words, to find a critical point, we're going to be setting the gradient equal to 0. So if you're finding a critical point, really you're saying the gradient is 0. Or in other words, you're saying that the direction, that there is no direction of steepest descent. Right? You can't go any, right? Because no matter which way you go, your derivative is just 0. There's no up, there's no down. So, let me say it again. Back up. So, to find critical points, of a function of two variables, we set fx equal to 0, fy equal to 0, and find all solutions. Or in other words, we set the gradient equal to 0. I should really say, I should be a little more careful with my word choice there. We set the gradient equal to the 0 vector, where each component is. So the 0 vector is not the same thing as the number 0. The 0 vector is the vector where all the components. I will also say the 0 vector is the only vector whose length is 0. Every other vector has a length that is more than 0. It's great. Okay, so look at some examples. Let's look at this first example. Our function is x squared plus y squared minus 2x plus 4y plus 3 equal to 0. So we want to find and classify, which we'll talk about in a second, all critical values. Cool. What's going on over here? So make sure all the people on Zoom have the attendance form. Here it is in case you didn't get it. So we're going to set each partial derivative equal to 0. So my partial with respect to x is 2x plus 0 minus 2 plus 0 plus 0. If I set that equal to 0, I get x equal to 1. And my partial with respect to y is 2y plus 4 equal to 0. So I get y equal to negative 2. So my only critical point, my single critical point, is the critical point 1 comma negative 2. The point where both partials are equal to 0 at the same spot. So 1, 3, not a critical point, right? Because if x is 1, great, but if y is 3, oh, not great, because the second partial, the other partial won't be equal to 0. So that's how we find critical points, where you have coordinates where both partial derivatives are 0 simultaneously. Okay, how do we classify them? So you might recall, you might not. Let me actually, so we'll come back to this in just a second, I promise. But you might recall back in 17a, you might have learned the second derivative test, which said something like, for example, if I have a function like x cubed minus 6x squared, and I want to find the critical points. Critical points set the first derivative equal to 0. You're going to get 3x times x minus 4 equal to 0. You're going to get x equal to 0 and x equal to 4. One way to classify those critical points is to use the first derivative test and to say, okay, make a number line, put those critical points on your number line, and check out what that first derivative is doing. And if I start plugging in, well, if I pick a number larger than 4 like 5, positive, positive. Pick a number between 0 and 4 like 2, positive, negative. Pick a number less than 0 like negative 1, negative, negative. So my function, since my derivative is positive, my function is increasing. My derivative is negative, my function is decreasing, positive, increasing. So using the first derivative test, we could have said that we have a relative maximum at x equals 0. We have a relative minimum at x equals 4. However, that's not really an option when you have functions of 2 variables. So instead, we're going to use an analog of what is called the second derivative test. The second derivative test saying, instead of looking at the first derivative, we don't really care. What we're going to do is we're going to say, well, if you check out the second derivative, you can also learn stuff. So my second derivative is, let's see, 6x minus 12. And the second derivative tells us about the concavity of the function. If the second derivative is positive, the function is concave up. Second derivative is negative, the function is concave down. So if I plug in my critical value, f double prime of 0, I get 0 minus 12, which is negative 12, which is negative. So at this critical point, which could be a maximum or could be a minimum or could be neither, but at this critical point, the second derivative is negative, meaning it's concave down, meaning at this point we have a maximum because my second derivative is negative. And in a similar way, at positive 4, we plug that into the second derivative, we get 6 times 4 minus 12, which is 24 minus 12, which is positive. So it's concave up, meaning we have a minimum. Here's what this function kind of looks like. kind of looks like this, where you have a relative maximum there at 0, 0. Oh, look, it's concave down there at 0, 0. At some point there's an inflection point where the concavity changes. And then over here, it's concave up, specifically at this point. It's a relative minimum. So here's the idea that we're going to extend to functions of two variables. If your function is concave up at a point, it's going to be a relative minimum. Function's concave down at a point, it's going to be a relative maximum. And then there's going to be a third thing, because basically the third thing is if it's concave up in one direction and concave down in another direction, like concave up in the x direction and concave down in the y direction, we're going to have a saddle point. So looking back at this example here, the thing we're going to calculate is not just the second derivative. It's actually this thing that's called the determinant of the Hessian. Here, it's not a big deal. Here's how people usually talk about it. They say we're going to calculate capital D, and it's equal to the second partial of x, I should say the second partial with respect to x, times the second partial with respect to y, minus the second partial, I should say minus the mixed partial, it doesn't matter which order, squared. For those of you longing to know, it's just the determinant of this 2 by 2 matrix. The 2 by 2 matrix of second derivatives, fxx, fxy, fyx, fyy. So the determinant of that would be fxx times fyy, which is exactly that, minus fxy times fyx, which is exactly that if they're the same, which they usually are. So you don't really need to know this, but it's good to be like, people are like, where does that come from? This is where it comes from. Okay, so here we're going to calculate it. We're going to get, let's see. So my second partial with respect to x is 2, not very exciting. Second partial with respect to y is also 2. And my second partial, or sorry, my mixed partial is 0 either way. That's equal to 4. So this determinant of the Hessian being positive means, and we'll write this down in a second. What this means is we have a maximum or a minimum. It's one of the two. And the way you determine whether which it is. So if this is positive, you have a max or a min. And the way you determine which it is by looking at the second partial, meaning you look at fxx. So fxx is 2, which is positive, meaning it's concave up. Fyy is also 2, which is positive. It's also concave. So they're both concave up. So you've got a minimum. Minimum because fxx slash fyy is positive. So just so you can see what this looks like, because it is kind of neat to see. Oh, that's not what I wanted. Sorry. Come back. I do think it's nice to see what these things look like, as you've noticed, I'm sure, over the time. So we got z equal to x squared. I know you can't see it yet. Plus y squared minus 2x plus 4y plus 3. So essentially, we have a paraboloid. Oops! Wow, where'd you go? Come on, go back over there. Right, clearly has a minimum there. And if you look in the x direction, right, I mean, I can't search, right? If you, for example, if you set x equal to 2, sure, if you look in the x direction, oh yeah, it's certainly concave up in the x direction. And if you look in the y direction, like y equal to 4, it is certainly also concave. Oops, that doesn't really cross it. -4. It's certainly, maybe certainly, yeah. You're going too big. It's, you can see it's concave up, kind of, yeah, right there. So it's concave up in both directions, meaning it's a minimum. We'll see something different when we have a saddle in a second. So here. But let's talk about what we need to check. Oh, Eric. No. So here's what's really great. So when we calculate this thing, yeah. So here's what we're going to say. So when we calculate D, which is fxx times fyy minus fxy quantity squared. Three things can happen. Thing one, if D, I'm gonna start with the easiest one. If D is negative, which wasn't the case last time, right? D was positive last time. But if D is negative, then we have a saddle point. Literally named because it looks like a saddle, like you sit in on a horse, or like you encounter if you're ever hiking and you like go up the hill, and instead of going over the hill, you can kind of go either direction and it can go up either way. That's a saddle. Or like, you know, like, not to be vulgar, but think of like the crotch of your pants, right? It's going down this way and up this way. That's a saddle as well. Your pants are a saddle. So if you're ever forgetting what a saddle looks like, think about your pants. The second thing that can happen is if D is positive, then you have a maximum or minimum. Check one more thing. So then we have to do more work. We have to do more inspection, I'll say, to determine if we have a maximum or a minimum. And here's the work. Here's what I want to point out first. Notice that fxy quantity squared is always positive. So if this whole quantity is positive, then you have something minus a positive thing. This had to have been positive. So I'm just going to say it one more time. Notice that if D is equal to fxy times fyy minus fxy squared is positive, then it must be true that fxx times fyy is positive itself. It also had to have been greater than whatever fxy squared is, but I'm not caring about that. And if two things multiply together and they're positive, can they have opposite signs? They cannot. Okay, so it's a problem. Okay, so if D is positive, then we know that fxx and fyy have the same sign. And so we don't have to check both of them. We only have to check one of them, like Eric was saying. So if D is positive, then we can say if either fxx is less than 0 or fyy is less than 0, we have a maximum because it's concave down. And similarly, if either, you don't have to check both, just check one, fxx is greater than 0 or fyy is greater than 0, we have a minimum. But just check one, because you only have to check one because of the same sign. Lastly, the sad part, if you happen to get that this quantity is equal to 0, then this test is inconclusive. That does not mean that you cannot determine what kind of thing you have. Let me give you a short example of that. There's a really kind of typical example that people use to say, well, look, you don't have to be, this test doesn't always work. That doesn't mean you can't say things. Let's say our function f of xy was equal to x to the 4th plus y to the 4th. So I'm going to find my critical values. My fx partial is 4x cubed. Set that equal to 0. I get x equals 0. My fy partial is very similar, 4y cubed. I set that equal to 0. I get y equal to 0. So my only critical point is the point 0, 0. Now let's calculate D. So I will also say the difference between this example and, well, our first example was not very exciting because all of our partials were constant, so there wasn't actually a place to plug in your critical point. But later examples, we'll see that you actually have variables showing now. But to calculate D, it's going to be fxx times fyy minus fxy quantity squared. And we're going to get, let's see, fxx is going to be 12x squared. Fyy is going to be 12y squared. Fxy is going to be 0 squared. So this is equal to 144x squared y squared. And if our point was anything other than 0, 0, we would be able to get a conclusive result. But here, if we plug in the point 0, 0 for D, we get 144 times 0 squared times 0 squared, which is 0, which is inconclusive. However, we're observant people. You can see things. X to the fourth plus y to the fourth. No matter what you plug in for x and y, other than 0, 0, the result's always going to be positive. Pick anything for x to the fourth is positive. Anything for y to the fourth is positive. X to the fourth plus y to the fourth is definitely positive, unless x and y are both 0. So we can just see, because we know how numbers work, that, oh, 0, 0 must be a relative minimum, because f of 0, 0 equal to 0 is less than any other value of the function. So sometimes when this test is inconclusive, you can still kind of figure out what kind of thing you have based on just things being always positive or always negative or something like that. It doesn't always work out all the time, but a lot of the time, if they ask you a question like this, you can figure out what's going on. Well, let's look at some more conclusive examples, because they do get more interesting. Okay, we got some. Yeah, sure. Okay, now we'll look at this one too. So let's look at this example. F of xy equal to 2x squared minus y squared plus 4x plus 6y plus 1. This one's also going to be relatively straightforward, but still worth doing. So let's find our critical points. Partial with respect to x is 4x plus 4, so that equals 0. You're going to get x equal to -1. Partial with respect to y is going to be -2y plus 6. So if that equal to 0, you're going to get y equal to 3. So again, we only have one critical point, which is -1, 3. And then to find the determinant of our Hessian, it's going to be fxx, fyy, fxy squared. Still not particularly exciting. Fxx is 4, fyy is -2, and fxy again is 0. So we end up with -8, which is negative. And when this D is negative, what does that mean? It's not a max, it's not a min, it's a saddle. So automatically, we know we have a saddle at the point -1, 3. Kind of looks like this. I mean, I could draw it for you, but I think it's nicer just to see what it actually looks like. Let's see here. Let me make this look a little bit nicer. 2 minus. 1 second. Ooh, saddles always look kind of wild. So here's what a saddle looks like. It's very saddle-y looking, right? There's a saddle right there. It's opening down one way. It's opening up another way. That's kind of the whole deal with the saddle, is that it opens up in one direction and down in another direction. Kind of cool. I like saddles. They're kind of. So let's look at some more examples. I don't want that example. Move on. Okay, for my other examples. I got lots of examples. We're just hiding out. Okay, cool. We got time. Oh yeah, we got time. So let's look at least one more example. Let's say we have this function, f of xy equal to 3x cubed plus xy squared minus 9x squared minus y squared. Before I get too carried away, let me glance back at your homework just to make sure I'm not doing anything super crazy. I think it seems reasonable for your homework. Yeah. Okay. So first thing we're going to do, find the critical points. And this one is going to be a bit more complicated in that we're going to have more than just one. So let's find our fx partial, which is, let's see, it's going to be 9x squared plus y squared minus 18x. And we set that equal to 0. That seems worrying at best. Let's look at the other one. Fy is going to be, let's see, partial to y is going to be 2xy minus 2y equal to 0. So good rule of thumb, whichever equation looks easier is the one you should look at first. To me, the second equation definitely looks easier, so I'm going to deal with that one first. So I have 2xy minus 2y equal to 0. Now, you don't really ever want to divide by a variable. So it's really not a good idea to be like 2xy equals 2y and then divide both sides by y, because then you're going to lose y equals 0 as a solution. Y equals 0 is definitely a solution here, right? If y equals 0, I get 0 minus 0 equals 0. That checks out. So instead, what we should do is factor. So I'm going to factor out a 2y left with x minus 1. So then I get two solutions. Y equals 0, x equals 1. And what I have to stress here is that the point 1 comma 0 is not a critical point, because it doesn't make both of these partials equal to 0 at the same time. It definitely makes this one 0, but if you plug in x equal to 1 and y equal to 0 into the other equation, you get 9 plus 0 minus 18. It's not 0. So I want to be super explicit about that, right? You don't get a critical point by just setting one equation equal to 0, even if you get x's and y's. So now what we're going to do is we're going to go back to this equation and we're going to check each one of these values in here. So first, we're going to set y equal to 0. Why did I pick one? Maybe I'll set x equal to 1 first. First, set x equal to 1. So I do that, I'm going to get 9 plus y squared minus 18 equal to 0. Or y squared minus 9 equal to 0. So y minus 3 times y plus 3. Or I guess you could bring the 9 over to the other side. That's probably what you should do. So we get y equal to plus or minus 3. So we just found two critical points. We have 1 comma 3 and 1 comma negative 3. Now let's look at the other thing. We're going to deal with y equal to 0. So y equal to 0, I'm going to have then 9x squared minus 18x equal to 0. And I'm going to factor out a 9x. So if I factor out the 9x, I'm left with x minus 2. So I either get x equal to 0, or x equal to 2. So the critical points I get here are x is 0, y is 0, and x is 2, y is 0. So I got 4 different critical points from this. And now we have to check each one of them to see if it's a maximum, a minimum, a saddle, or neither. Or I mean, I shouldn't say neither, I should say, or not determined by it. Okay. So we got to calculate capital D, determinant of the Hessian. So let's see. Let's look at F. There's fx and fy. D is going to be, I do think it's worth your while, at least the first few times you do this, to actually write out what it is. Fxx, fyy minus fxy squared, just to kind of get in the practice. And if you write it out enough times, you'll just remember what it is. So let's see here. Fxx is going to be taking the partial of this with respect to x. I'm going to get 18x minus 18. Fyy is going to be, let's see, partial with respect to y is going to give me a 2x minus 2. And then the mixed partial with respect to of x with respect to y, or y with respect to x is going to be, let's see, I'm going to do this one. Fyx should be 2y. That seem right? Yeah. Fxy should be 2y. Okay, and I don't really think we want to simplify this, but here's what you might do if you want to make it a little easier to calculate. You might rewrite this. I might factor out the 18 from here, leaving with an x minus 1. I might also factor out the 2 from here, also leaving with an x minus 1. That was kind of coincidence. So I might rewrite this as 18 times 2 is 36 times x minus 1 squared minus 4y squared. That's just going to make it easier to plug in my various values. But again, not really necessary. Also, not super necessary to actually find what the value of this is. You just have to be able to tell if it's positive or negative. So if I'm going to plug in 0, 0, for example, I'm going to get 36 times 0 minus 1 squared minus 4 times 0 squared. And let's see, 36 times 1 minus 0, that's for sure positive. Ooh, I will say one disadvantage to what I've done here. It's not a huge disadvantage, but it is a mild. This does kind of obfuscate what our, whoops, come on. That happens when you press too hard in your stomach. Okay, so actually, I think it was my button. Anyway, this kind of hides what fxx and fyy are. So it's probably good to go back and be like, oh, look, that's my fxx, and that's my fyy. Because if d is positive, that means we have a max or a min. We have to check. So I'm going to check either fxx or fyy. Fyy at 0, 0 is 2 times 0 minus 2, which is negative, meaning we have a max. Concave up. Sorry, geez, I said the wrong thing. Concave down. Right, you have a minimum if it's concave up, it's concave down, we have maximum. Okay. Then we do it for the other one. So then we have the other critical points. Let's see, we had also 2, 0. So plugging in 2 for x and 0 for y, I get again 36 times 2 minus 1 squared minus 0. And again, it's going to be positive. And now if I plug that into my either of my second partials, fyy at 2, 0 is going to be 2 times 2 minus 2, which is positive, meaning we have a minimum at 2, 0. Keep going. So then we're going to plug in our other critical point, 1, 3. Plugging in 1, 3, 1 for x, 3 for y. I'm going to get 36 times 0 squared minus 4 times 3 squared, which is going to be a negative number. It's going to be negative 4 times 9, which means we have a saddle. And then the same thing's going to actually happen with our other critical point, because other critical point is just the same, but the y value is the negative of what it was. But squaring a negative or a positive number is going to give you the same output. We get negative 4 times negative 3 squared, which is also less than 0. So we also have a saddle there. 2 saddles, 1 max, and 1 min. I feel like maybe a little hard to visualize, so I would like you to see it just because I'm not gonna lie. I think these things just look cool. I think they're interesting to see. So if we take a look at this one, z equal to, where'd you go? 3x to the third. Double, come on. 1 second, 3x to the third plus xy squared minus 9x squared minus y squared. Oh, come on. 1 second. Oh, that looks wild. I did some weird funky thing where it's like giving me all this. Well, let's take a look. You can, whoa, okay, come back. So you can kind of see, maybe not. I've grabbed it in the wrong way. Impossible. I'm sorry. We're done for. We really are done for. Sorry, I've broken it. What you do when you break it is you hit the little home button. There we go. So you can kind of see there's your relative maximum. And if you zoom out a bit, it looks kind of super funky. It looks really funky. It's not very easy to see. I would encourage you to deal with this one on your own at some point, because I've definitely graphed this one other times and be able to see what things look like, but yeah, this one looks kind of wild. It's not giving you what I want. But we can definitely see the maximum. There's a maximum for sure. There is also the other things. I'm just not getting the graph how I would like it to look, unfortunately. Disappointing. That's not helping.
So the more critical points you have, the more like you have to check.
Right. So what I should say is for every critical point you have, if you're being asked to, if the typical kind of question is find and classify the critical points of this thing, for every critical point you find, you have to plug it into this capital D and determine if it's a maximum, a minimum, a saddle, or inconclusive. Yeah. The ones on your homework I don't think are quite so intense as this. Yeah, they're pretty reasonable. Yeah. The last one looks a little loud. We do more? Do one more. So let's look at let's do one more like this. Let's say we had something like f of xy equal to, sure, 7xy plus 6x squared minus 9. We want to find the critical points. They're probably going to be terrible if we just made it up. So you all find the partials. Oh, it is going to be terrible. Not really. It's not really terrible. All right, I think this problem makes a really good argument for dealing with the easier one first. So even though it wouldn't be that hard to kind of figure out what's going on here, you wouldn't actually be able to get a point with just this equation. You could solve for, sometimes you do have to like solve for y, or you could solve this for y and get y equal to negative 12.7x. And then, okay, well, my critical points are on some line. But really, if we deal with this part first, we're just going to get x equals 0. And if you plug that back in up here, you're left with 7y plus 0 equals 0. So also y equals 0. And a lot of the time, not always exclusively, but frequently you do get 0, 0 as a critical point. Sometimes your only critical point, sometimes one of many. But that's our only critical point. Then we do the usual thing. We find fxx, fyy, minus fxy, quantity squared. Probably not super exciting. Probably going to be just constants. Fxx is 12. Ooh, fyy is what? 0. And then fxy is it 0? Is it 0, 12, or 7? Definitely 7, right? And also, if you weren't sure, you also check fyx. Oh, fyx is also 7. It is 7. I should say, not that that's always 100% of the time true, but like unless you're encountering some super bizarre function, it should be true that fxy equals fyx. We shouldn't be encountering anything in this class where they are not equal to each other. So you have fxy not equal to fyx. The first thing I would say is check your work. And then the second thing I would say is if you're really convinced they're not equal, it better look super freaky. And come see me because it's probably not. So here we're going to get -49, which means we have a So that's pretty much all there is at this point to classifying relative extrema of a function of two variables. Either relative maximum, relative minimum, or something. Next time, assuming that's where you guys are headed, we'll talk about finding absolute extrema on a closed boundary. So you could have some function that you're just cutting off at some point and saying, well, where is it the biggest? Where is it the smallest? And you can find a point because there's always some like n to it, essentially. It's kind of like looking at something like this. And saying, where is this function that I've limited to just from here to here? Where is it the biggest and where is it the smallest? Oh, well, it's the biggest right there. And it's the smallest right there. That's kind of the idea. It's just a little more complicated when you have functions of two variables. That's really what we're going to be doing, is saying you've got some function of two variables, some surface, and you're then kind of taking scissors to your surface and cutting part of it and saying, okay, on this part I've cut out, where's the highest point? Where is the lowest point? All right.